Okay, so today we're going to look at something called a one proportion Z interval. It's a way of estimating the population proportion for a particular parameter. So let's take a look at this problem. It's about Tanya, and she wants to estimate the proportion of her school senior who plan to attend the prom. She interviews a simple random sample. That's what it says here. So we have an SRS of 50 people. So N is 50 of the 750 seniors that go to her school, and finds that 36 plan to go to the prom. So sometimes we call that X the number of people that plan to go to the prom. And from these two numbers, you can calculate P hat, which is the sample proportion of people who want to go to the prom in her school. That's 36 out of 50, or 0.72. So part A asks us to identify the population and the parameter of interest. The population is the 750 seniors in her school, and the parameter of interest is the proportion of her school seniors who plan to attend the prom. So it's good to identify those things. Part B, checking your conditions for constructed confidence interval. It's the same thing as you were doing a one proportion Z test. So let's go write those on a new page. Number one, you're supposed to have done a simple random sample, which was stated. Number two, the independence check. So your population of all people at the school should be greater than or equal to 10 times your sample size. And usually in problems, they don't tell you the population size. You have to kind of assume it's big. But here they actually told it was 750 kids. That's pretty good, which is definitely greater than or equal to 10 times 50 or 500. So we can check that off. And because this is true now, you can use your standard deviation of p hat formula. Now, there's one subtle difference when you're doing a one proportion Z interval compared to a one proportion Z test. You might remember this formula from before, having the following. You might say standard deviation of p hat equals the square root of p times 1 minus p over n. But that's only if you're doing a one proportion Z test, and that would be because you have an HO which states what p equals. That's not the case in a confidence interval. We don't have a null hypothesis, so the best we can do is use our p hat here. So that's an important difference now when you're dealing with confidence intervals. Okay, and then finally, you're always supposed to check for normality somehow. So how do you do that in the case of a one proportion Z test or a one proportion Z interval? Well, you have to check that n times p hat and n times 1 minus p hat are both greater than or equal to 10. So in our case, we'd have 50 times the p hat, which is 0.72, which is 36. That should not surprise you. And then you have 50 times 0.28, which is the other 14 people in the sample. So these are definitely both greater than or equal to 10. We could check that off, and that means that p hat is approximately normal. So we're ready to proceed and calculate our intervals. Let's go back to the problem because that's what it's asking for in part C, asking us to construct a 90% confidence interval for the proportion. Okay, so the confidence interval has a familiar format to us. Here's how it looks. Our old confidence intervals for means were x bar plus or minus t star s of x over rad n. So that's what you do when you're looking for means. In the case of proportions, you have p hat plus or minus z star times our standard deviation formula, which is different in the case of a proportion problem. So it looks like that. All right, so we're ready to fill these things in. This is 0.72 plus or minus. We'll leave that blank for a moment. And this is going to be the square root of 0.72 times 0.28 over 50. And what we also need is we need that z star that goes in here. So to do that, we draw a normal distribution. We put 0.9 in the middle. And then we ask ourselves what area is in the tail here. And so if we were to do a little math, we know this is 1 minus 0.9 over 2, or just 0.05 in each tail because of the symmetry that exists in a normal distribution, right? So this tail over here is also 0.05. All right, so we just need a z-score that goes there. You can use inverse norm if you like, or you can use the z-table backwards, look for the area of 0.05 in the table and ask yourself what z-score goes with it. If you do that, you will get negative 1.645. We'll put the positive version of that here. And there you go. So this thing technically is your confidence interval. You have to do a little bit of computations. So let's go to a new page and write out what the answer is going to be. So if you do the calculation, you'll get 0.615, about that, might round differently depending, and then over here up to 0.8244. So this is the 90% confidence interval. So we can interpret that by saying the following. We are 90% confident that the true proportion of students at Tanya's school who want to attend the prom is somewhere between 0.615 and 0.8244. Let's just for comparison's sake remind ourselves again. Let's check out the 95% confidence interval. Just remind ourselves what would be different there. You would still have the same p hat. It'd be plus or minus. You're going to have a different z star now. Your standard deviation will not change, but your z star is different because when we look at our normal distribution here, we've got an area of 0.95 in the middle, and you need to know what's in the tail. So this is only 0.025. So when you do inverse norm, you'll get a z star now of negative 1.96. Notice it's really close to 2. We've used 2 in class, but in most textbooks, or if you went looking other places online for help, you would see 1.96. So I'm just going to leave 1.96 there. Let's see what this confidence interval, let's see what all this turns out to be. You should pause the video and ask yourself if you think this interval is going to be wider or narrower than the one up here. That's a good question. Can you answer that? Okay, so you should have gotten 0.5955 up to 0.84445, something like that maybe. Notice it is wider. You shouldn't be surprised by that. If you want to be more confident that you've captured the true mean, then you need to use a larger confidence interval. The one on top here that here we go with the stars, that's the smaller one. It's more narrow because we're only 90% confident the true proportion lies in that interval. And with regards to this one, it would be something wider because we're more confident that we've captured the true mean. Okay, great. Thanks for watching.